Good afternoon. My name is Ahmad Fahmi Haryono with the number 22055311136 from Engineering Faculty of Mechanical Engineering, Udayana University. Today we're gonna talk about linear equation and matrices. Section 1.5 Matrix Algebra. Mathematical proof is a lot more powerful than scientific proof because it is not subject to experimental data, and the result is absolutely correct and permanent. For example, we often use the identity x plus y squared equal to x squared plus 2xy plus y squared, but this is not truly simply because it works for every example we try, but because we can prove this result. Once you have proven the general result, x plus y squared equal to x squared plus 2xy plus y squared, then you don't need to worry about trying it for particular number, because you have no doubt that the result is correct. 1.5.1 Properties of matrix addition. Zero matrix. What do you think the term zero matrix mean? A zero matrix is a matrix which has all zero entries and it is denoted by 0, the 2 times 2, 2 times 4 and 3 times 3. Zero matrix are like this. Theorem 1.12 Properties of matrix addition. Determinant A, B, C, B matrix of the same size m times n, m rows and n columns. Then this one. Next, 1.5.2 Properties of scalar multiplication. Theorem 1.13 let determinant A and B both be m times n. Matrix and C K be scalar, then CKA equal to CKA. This one example, determinant A and B. Next, 1.5.3 Properties of matrix multiplication. The algebraic rules of matrices are closely related to the algebraic rules of real numbers, but there are some differences which you need to be aware of. Matrix multiplication is not commutative, which means that the order in which we multiply matrices matters. If A and B are matrices, then in general, A times B not equal to B times A. Example, like this, the solution. Next, 1.5.4 Matrix power. Matrix power are particularly useful in Markov chains. These are based on matrices whose entries are probabilities. A Markov chain is a sequence of random variables with the property that given the present state, the future and the past state are independent. What is a square matrix? A square matrix has an equal number of rows and columns. So, any n by n matrix is a square matrix. Determinant A be a square matrix. Then we define like this. Section 1.6 The transpose and inverse of a matrix. We should now be familiar with matrix operations such as addition, subtraction, and multiplication. What about division of matrix? You cannot divide matrix. The nearest operation to division of matrix is the inverse matrix, which we discussed in this section. We can use the inverse matrix to find solution of linear system. There are other important operations of matrices such as transpose. 1.6.1 Transpose of matrix. What do you think the transpose of a matrix might be? It is a new matrix which is made by rotating the rows of the given matrix, for example 1, 3, 5, 2, 4, 6, then transpose to 1, 3, 5, 2, 4, 6. 1.6.2 Properties of matrix transpose. Properties of matrix transpose. Determinant A and B be matrices of appropriate size so that the operation below can be carried out. we have the following properties. For example, determinant A, 3 minus 4, 1, 5, 2, 6, transpose to the same. Next, 1.6.3 Identity Matrix. What does the term identity matrix mean? The identity matrix is a matrix denoted by L, such as AI equal to A for any matrix A. This is similar to real number where the number I is the identity element which satisfies x1 equal to x for any real number x. What does the identity matrix look like? It is a matrix with I along the leading diagonal, top left to bottom right, and zeros elsewhere. For example, like this: 1, 1, 1, 1, 1. 1.6.4 Inverse matrix. What do you think an inverse matrix is? Given a square matrix A, then the inverse of A is a square matrix B such that A times B equal to 1. Why is the inverse matrix is important? We wanted to use matrix to solve system of linear equation, which we can generally write as A times x equal to B, where x is the vector of unknown that we wanted to find. If we multiply both sides of this A times x equal to B by the inverse of matrix A inverse, we obtain like this. Hence, we find the unknown by finding the inverse matrix because x equal to matrix x equal to A inverse times B. So this is the example. This is how we solve. 1.6.5 Properties of the inverse matrix. Proposition: the inverse of an invertible matrix is unique. What does this proposition mean? There is only one inverse matrix of an invertible matrix, or mathematically, there is only one matrix B, such that A times B equal to B times A equal to 1. We suppose there are two inverse matrices associated with an invertible matrix A, and then show that these are in fact equal. Let's nominate this inverse matrix as B and C, and show that B equals to C. This matrix B and C must satisfy A times B equal to 1 and A times C equal to 1 because B and C are inverse of A. Since both A times B and AC are equal to the identify matrix 1, we can equate them. A times B equal to A times C. Multiply this equation A times B equal to A times C by matrix B, like this. Section 1.7 Types of solution. In this section, we examine more complex linear system which involve many equations in many variables. We try to reduce this linear system to their simplest possible form by breaking them down to reduce row echelon form. 1.7.1 Equivalent system. What does row equivalent means? Two matrices are row equivalent if one is derived from the other by applying elementary row operation. In a linear system, is described by the augmented matrix AB, and it is row equivalent to R B. Then both linear systems have the same solution set. 1.7.2 Types of solution. There are three types of solution to a linear system. Number 1, no solution, unique solution, and infinite number of solutions. If the system has no solution, we say it's inconsistent. 1.7.3 Homogeneous system. A homogeneous linear system is defined as A times x equal to 0, where A is an M by N matrix and X is a vector. What does the term homogeneous mean? A linear system is called homogeneous if all the constant terms on the right hand side are 0. That is Ax equal to 0. Then this equation can be removed without affecting the solution. A row with all zeros entries is called a zero row. 1.7.4 Non-homogeneous system. A non-homogeneous linear system is defined as A times x equal to b, where b not equal to 0, to O. Here, at least one of the b's must take a value other than 0. Proposition 1.32, let a consistent non-homogeneous linear system Ax equal to b, where b not equal to O, b row equivalent to the augmented matrix, where R in the reduced row echelon form, and there are n unknown and r non-zero rows in R. If R less than n, then the linear system Ax equal to b has an infinite number of solutions. Section 1.7.5 Application to puzzle. We can use Gaussian elimination to solve puzzles. We can solve Sudoku puzzle by using this technique. Most of the people think that they have no choice but to solve this puzzle by trial and error. But applying Gaussian elimination provides a general solution and is done systematically. This is the example. Next, section 1.8, the inverse matrix method. Another way to solve the linear system Ax equal to b, where A is invertible, is to use the inverse matrix. However, finding the inverse of a matrix is a long process, and we can often solve linear system quickly using Gaussian elimination. So, why do we want to find the inverse matrix? The inverse matrix is not useful for solving a linear system Ax equal to b, but it is useful if one needs to solve many systems that have the same coefficient matrix A. Elementary matrix. An elementary matrix is a matrix obtained by a single row operation on identity matrix 1. Equivalence statement. You will need to look up what is meant by reduced row echelon from ref, which was defined to understand this subsection. What does the term equivalence mean? Two statements P and Q are equivalent if both P and Q are true or both are false. Another way of saying this P if Q denoted by P and Q, this means that P implies Q and Q implies P. Determining the inverse matrix. What does this mean? It means that the same elementary matrix E1, E2, E3, and EK transform the identity matrix 1 into the invertible matrix A inverse. This actually implies that we have to perform the same row of operation that transform the matrix A to the identifier matrix 1, and also transform 1 to the inverse matrix A inverse. Summarizing this. 1.8.4 Solving linear equation. Consider a general linear system which is written in matrix form as Ax equal to b. This one, here's the solution of linear system Ax equal to b, where A is invertible is given Ax equal to inverse A times b. Theorem 1.38. Determine A be an n by n matrix when then the following 5 statements are equivalent. The first is the matrix A is invertible. The linear system Ax equal to O only has the trivial solution x equal to O. The reduced row echelon from the form of the matrix A is the identity matrix 1. A is a product of elementary matrices, and the last, Ax equal to b, has a unique solution. 1.8.5 Non-invertible singular matrices. If the above approach of trying to convert AI into the augmented matrix I inverse A cannot be achieved, then the matrix A is not invertible. This means that the matrix A does not have an inverse. By the theorem 1.38, we know that the matrix A is invertible. The reduced row echelon from A is the identity matrix 1. Remember, The reduced row of echelon form of an n by n matrix can only 1. Be an identity matrix, or 2. Have a row of zeros. Proposition 1.39. Determinant A be a square matrix and R be the reduced row echelon from A, then R has at least one row of zero. A is non-invertible or singular. 1.8.6 Application to cryptography. Cryptography is the study of communication by stealth. It involves the coding and decoding of message. This is a growing area of linear algebra application because agencies such as CIA use cryptography to encode and decode information. One way to code a message is to use matrices, like this one. This is the example of cryptograph. That's it for today. Thank you.